Okay, at 6 o'clock. Boy, our class size is dwindled. Preparing to record. If you don't hear me say that at the beginning of the class, I'm not saying that to hear it to myself, that if you don't hear me say that, that means I forgot to hit the record button. Recording. Duration's 4 seconds. Okay, we're on. Okay, so here's the data for, I think 6.8. It's just some time pressure data. I don't make you guys type this in because we don't have to worry about errors, and I've already got it typed in. So we will look at just stripping that in to our example 6.7. Who can tell me what the big difference between 6.7 and 6.8 are? This is a buildup. That's exactly right. You're on your way to an A. And I'm going to have to steal an equation from my textbook, so let's get that up there too. Where do I have that? This is where I cannot use the snippet tool. And I don't understand why I don't have, maybe I just don't know how to use this. It's kind of fun though. Okay, we are in, this doesn't look familiar. There's some type curves. That's chapter 8. Anybody ever look at chapter 8? That's chapter 3. Oops, there we go. As soon as I see the Cincolay diagram for different kinds of flow regimes, I know I'm getting close. We're going to use a new equation, and we're going to replace this equation right here tonight. Now, remember, we didn't have to do this in the last class. By the way, we're going to do our exercise first, and then we'll do our look at the test key second. We'll take a little break between the two. But I feel like some of the problems that we're having will be taken care of as we look at using a drawdown template and converting it to a build-up template. Okay, hear what I'm saying? And then also, this is really one of the only really hard things to find, is this is our Agarwal effective time for what type of flow? Radial flow. Now in here somewhere, and I'm not going to be able to find it immediately, but I know it's at the bottom of the page on the right hand side, is the Agarwal effective time. In other words, accounting for superposition for the time the well produced. You with me? Okay, so let's find that because we're going to need that equation tonight.
Can I ask a question about different time variables?
Yes.
And this was something that we had talked about briefly before the test last week, trying to understand the significance and using both the pseudo time and the Agarwal effective time. My understanding was that the pseudo time, it compensates for
Viscosity and compressibility.
Yeah, basically gas versus.
And what does Agarwal effective time account for?
It accounts for earlier production.
It accounts for the fact that we're doing a buildup and is superimposing the pressure drop that would happen at a time as if it was a drawdown instead of a buildup.
Okay.
So do we have to do one or the other or both, always?
Well, we have pseudo-time.
Always.
Because we have to, so what I'm saying is when we do aggregate well effective time, do we do that as a function of the pseudo-time?
Yes.
Okay.
Good question. Although I looked at your last test, and if you failed to do pseudo-time, your errors in your results are not going to be significant. It usually, in general, has little effect. Maybe a 10% error in your number. But you pretty much do it. It's easy. I mean, if you got a VB function and you just strip in a column, it's not hard to do. Okay, so we're searching for... Yeah. I can't hear you. You guys got to understand, I got a rack of machines in here just roaring into my ear. You're going to have to shout.
Okay, I'll take you back a little. As regard the bilinear flow, does it only exist when we use water as a fractional fluid? You said something about I was going to the video also. The bilinear flow, does it only exist when we use water as the fractional fluid? So when we start producing gas, during the process, you said something about the gas will be, the water at first will flow out of the formation before there will be a constant flow of the gas. So you were trying to explain that this is the bilinear flow. I'm assuming we use gas as the fractioning fluid. Does the bilinear flow exist?
Okay. I'm not directly answering your question, but I'm going to tell you everything I know. Okay? Is that fair? We're actually going to work an example, and it might be this first one tonight or it might be the next one, where we're going to have a bilinear flow period. Okay? It's synthetically generated from a simulator that doesn't have any water in the fracture. So the data that we're going to look at in this textbook when we look at bilinear flow is fictitious. The only situation where you would ever look like something that would be that way in the field data is if we did a propane frac, where we actually had the same phase, maybe not exactly the same composition, but the same gaseous phase in the fracture as we did in the formation. And when we saw the formation flow coming into the fracture and then coming along the fracture to the wellbore, we wouldn't see any relative permeability. Are you ever going to see that in your life? Probably not. Okay? But we'll look at it when we look at bilinear flow from this textbook. But again, it's not field data. It's synthetically generated from a simulator that it only has single phase. And I'll give you an example. We're actually trying, my little research group, is actually trying to figure out how much frac water we actually get back. Now we're back to water fracs. So what we do is we build a grid system and we fill it full of gas, and then we build a fracture that has higher permeability, right? And we fill it full of water, and then we figure out what that pore volume of water is, and we figure out the pore volume that is going into a fractures treatment, like 1 million barrels, and the first thing we do is we actually inject water in our simulation before we start it up. And so we're simulating not only the production from a well, but the injection of water into the formation. And so then when we flow back our simulator, it's a drawdown, and I get vastly different gas production rates than this textbook would have. It actually starts off low and builds. It doesn't decline, it builds. And why is it building? It's because the gas saturation is increasing, so the relative permeability of the gas is increasing. Because it's starting with 100% water saturation. When you get done fracking, the only fluid in the fracture is water. What's the relative permeability of the gas in the fracture? 0. Okay? Is this helping? Okay. So in reality, and I'm very familiar with this because in our study group, that's what we're doing. We're filling the water with fracture. So I mean, if I was going to run a simulation, and then part B of my story is that it's going to be very difficult to analyze bilinear flow. I tend not to use bilinear flow because the regime is masked by two-phase production. And so I don't use the term. It's still a period of time where I'm simultaneously flowing from my formation into my fracture and my fracture to wellbore. That concept is still there, but the performance that I would expect with single phase doesn't exist. So I like to just call it cleanup, okay? And I wait for cleanup to be over with, and then I usually move on to analyzing formation linear flow, which is the next flow regime after bilinear flow. So we'll do exactly what the textbook tells us to do to analyze bilinear flow, but it's synthetic data from single phase simulations. And again, the only way that you'd ever see that in the real world is with a propane frac or a CO2 frac. Does that sufficiently answer your question? Good, because I think I put that information out before, but maybe that's a little more succinct. Okay, we're looking for an equation, and we're looking for my glasses. Okay, it's in this region right here on one of these pages. Make a lot. Oh, here it is. Here, we're just now getting into linear flow. If I get to the end of the chapter, I went too far. Maybe somebody can find it faster than I can. I'm looking for the Agarwal effective time for linear flow. And, you know, I have spatial memory that tells me where it is on the page, and I think it's on the lower right hand of the page.
It doesn't tell you the one for linear and the one for radial in the same space?
No. This chapter covers, and see, now I'm in dual porosity. I think I've lost it. It's way before this. Does it got a T sub P in the denominator? Yeah. No, that's not the one we're looking for. What page? Page 446? 146. Okay, that's about where I am. That sounds good. It's buried in a paragraph. I don't see it on 146. There's the Agarwal type curve. It should be post-fracture. It should be right where we're at because we're doing a post-fracture. That means the well's hydraulically stimulated. And if we're doing a build-up, we're going to need Agarwal effective time for this example. Do people have to throw up or something? During the break, I'll have to go up and get my textbook because I got it highlighted and it's easy to find. It's buried in a paragraph. It's not like an equation, but with an equation number, as I recall. That's the radial Agarwal equivalent time. There's a linear flow Agarwal, and it's below. It's before we get to. I thought I'd find it by now. We may have to just move on and get it later. It should be right at the very beginning of. If it says log, what type of flow regime are we in? What? Remember, log. Radial, square root of time, linear. It's going to have. It's not going to have any logarithmic terms in it. Watch, make a liar out of me. It will. Haven't we already looked on page 141?
Yeah, but this is kind of hidden. It says prepare linear flow and definition of.
There it is. We found it. According to Economides, for a build-up test, Agarwal's equivalent function, delta TE, which is the one that we have the numerator and denominator, is used in place of T for the definition of dimensionless time. However, this definition of delta T applies rigorously only for radial flow in an infinite acting reservoir. For pure linear flow, the definition of equivalent time, delta T equivalent, I don't know what the N stands for, linear is T sub C, we got square roots. Okay, so I'm going to do a print screen. What is that, Gina? Function spacebar? Correct. 141. 141. Okay. I'm just going to paste it before I do anything else. Okay. Now I'm going to take our drawdown and I'm going to make it a buildup. I'm going to move or copy, create a copy, and move to the end, and we're going to make this 6.8, right? And then I think I have my snippet tool, right? It's on my desktop. Voila. We are going to need this one equation. And I'll just insert a column right now and paste it up here. Okay. That was a lot of work to get this done. Okay, so we're going to convert a template that we've made for linear flow drawdown to a linear flow buildup. Okay, so let's get our data in. And we have our data under delta T in PWS. Let's see, are we set up to, do I have to make 2 copy paste or 1? Time pressure, I just have to make 1 copy paste.
So did you copy your 6.7 and entirely new page?
Yeah, I copied 6.7, renamed it 6.8, and I'm going to make that my new template for a linear flow buildup. In fact, you know, well, let's get our stuff copied over. Okay, so at delta T equals hours, we have a flowing pressure, or a well pressure of 4664. Copy. And that's all I'm going to get from this thing, and then I'm going to come over here and I'm going to paste those values. And I'm going to be very careful here. I'm going to go down here to see what's at, where my gray ends at 168 and see where my counting starts over. I'm going to delete all this stuff because this is data that went with the last problem. Okay? You with me? Oh, I can't change an array. Here's what I do when I like this pseudo time function and I can't change it. Here's what I do. I drag it up, and so I have a copy of it. See that? I have a copy of it. And then I delete the array. It says I can't change any part of array. I can't delete it. Why not?
Yeah, it's got a pointer. We're going to use the build-up version.
You guys are so good. Okay. Now I got to come down here and delete my data. It ended at what? 168. Okay. Now I can come back in with this array and it's going to grab my time and pressure. The array's too big, and it's actually the wrong function because remember I got a build-up function. I can get rid of that now. I need T sub dA build-up, right? Not T sub dA drawdown. So this didn't help me to do any of that work. I got to start over anyway. My pseudo time for drawdown already knows what my average system reservoir pressure is. It's the first pressure in there that I'm drawing down from. But on a buildup, I don't know what that is in advance always, and so this 4664 is not going to work. We need to go to our textbook. Okay, let me copy paste or cut paste the whole problem in here. This is on page. Our problem is on page what? That makes you mad. Well, we're doing 6.8, and so they give us, there's nothing we can work with because everything is going to include viscosity. I bet you if we just assume that, boy, it makes me mad I can't, I'm not going to do a big copy paste here. I say that, and yes I am. But I want to do it so I don't get too much extraneous. Oops. Okay, I'm over here. I may have to go back to that page and get some other stuff. But it says that the initial pressure is 5,000 pounds. That's all I want to get right now. That's the only number I want to get, and then I'm ready to do TA. Because it equals, and some of you said that you didn't have this, pseudo time buildup. My time and my pressure and my gas gravity. You know, I may not have the right gas gravity over here right now, but when I change it, it'll change my values in my array. How do you know that? Based on viscosity? It's just that, remember, I can repeat over and over again that I know that this textbook uses a different viscosity than I use. If you could do it with a B sub G, or because we use the book and I use the same Z. See, this is the only reason I copied over PI, 5,000. And do those have to be absolute when I don't think so, no. It just gives me the rest of the numbers. Now I got a TA of 0. Now I can F2, Control Shift, Enter. And my 168 becomes a bigger number, it becomes 319. I basically double most of my numbers. Okay, is there anything else we need to correct over here? Let's look at this data right here that I'm wiggling around here. Porosity is 20% instead of 10%. See that? You see, Gene, you should be able to get my reservoir temperature from, no, not from that. Nothing, B sub G. Well, let's get gamma. Oh, I see. We're not going to be able to get them both. So, this is going to be a rough one. This is the kind I'd give you for the final exam. You don't have any gamma, and you don't have any temperature. So let's figure it out, okay? What else can we get here? We got a rate, 1,000 MCF a day. Height is 100 feet. Okay. I know on the next page, but let's get this stuff in here right now. They're giving me a B sub G in reservoir barrels per MCF, 0.6992. This is a good number to work with. And that gives me it in the units I like, okay? And then my B sub G is going to be a function of temperature, pressure, gas gravity, and composition. And if we were going to solve on something, we would like the difference between their B sub G, I forgot my equal sign, equals open paren their B sub G minus my B sub G divided by one of the other B sub Gs. So that's an error. Ooh, wow. 99%? Oh, I grabbed the wrong units. Okay. So just using 200 degrees and 0.6, I only got a 4% error. See that? You know, if my boss was breathing down my neck for an answer, I would just continue. I would say that's good enough. But since you might get points taken off on the final, maybe we should try to get. Let's go back to our textbook and see if there's some more clues. Oh, we're going to need this T sub P of 168 hours, aren't we? We're done with that. Hang on. Okay, T sub P. We don't have a column in our thing for T sub P because we did a drawdown. See that? We got to make room for T sub P here in our data. Typically what I do is scoop this stuff down and make room. I'll copy something that's already subscripted, and I'll put a T on one side and a P on the other side, and I'll delete the middle, and hopefully I'll end up with what I want. Time produced is 168 hours. PWF, I don't have to write that down. I already got that. See, that's at 464. We draw a well down, and then we build it back up. On my delta T scale, at time 0, I'm getting this 4664. Everybody with me? Okay. It was actually the last flowing pressure. It's also the first shut-in pressure. Well, it's the shut-in pressure at time 0. So regardless, my heading's right. It's the pressure of the well. 4664. So I don't have to write that down anywhere. It's already written in. RW is 0.25. Same. I don't really like that 0.002442 is not that useful to me because I know the textbook's using different viscosity. Let's see if there's any more clues in our textbook. Isn't there a table of I got to tell you, I think that the textbook does not accurately do adjusted time right, because my numbers get bigger and their numbers get smaller. Adjusted pressure is just pseudo pressure times a constant. There's nothing there I can really regress on. And then we get data for example 6.9. I don't think there's any more clues. I think we're going to let well enough alone with 200 degrees and 0.6. There is something in here, and this is a post-frac buildup. There is something we need from our textbook, and that's in the problem statement. Who can tell me what's important in that problem statement? Okay, well, okay. That's right. And that's why we grabbed a linear flow template. We digested that piece of information. Huh? Yeah, we have a prefractured K. So he's basically telling us, because it's Wattenberger and Lee, he's basically telling us that you're not going to have any radial flow. Remember that first one had a linear flow and a radial flow regime, so we were able to get the radial flow. We got a perm. We used that perm and got into our square root of KXF, and we could get an X sub F. We're not going to see any radial flow. I know that because I've worked this example, but he's also telling us that. That's why he's given us the perm. Now, where am I going to put that 0.1 millidarcy? I am going to put it right here because my template, my worksheet, already utilizes that space holder to calculate the x sub f from the square root of kxf. Okay? Now, this square root of kxf is some function of some slope somewhere, and I haven't determined if that's right or not yet. But that's where I'm going to, then typically I'd insert a comment, given in problem. Okay, and we have no idea what skin is, because we don't have that flow regime. Okay, I think I've got everything I need out of the textbook. I'm going to delete that. What happened to, oh, yeah. And I'm going to delete that. Okay. All right, so I have example 6.8. I'm building a template for linear flow for a buildup. What would I want to look at first? Who's got an idea? If I wanted to graph something, am I ready to graph anything? Huh?
Horner time? Do we have?
Horner time is for what flow? What kind of flow?
That's only for radio?
Yes.
Okay.
Now we have, but this is a perfect question. We have an equivalent to Horner plot. I just never know how deep to go. I don't think this is in the book. This is called an MC plot. And it's pressure if it's oil, and it's pseudo pressure if it's gas. And we'll get some early data that may be in line, may not, and then we'll get a straight line. And just like a Horner plot, as delta T approaches infinity, the amount of time I shut in the well approaches infinity, what does this equal? What do you think this indicates? Yes. And via pressure 1, we can get initial pressure. I don't think this plot's in our textbook. Okay, let's make that.
So on the X there, is that your Agrawalt time?
No. Just like Agrawalt equivalent time is not exactly Horner time. The form looks similar. And there's going to be square roots, there's going to be T sub P's and delta T's. They're not, so basically, we got radial and we got linear. We have specialized plot, and we have type curve. For the specialized plot for radial flow, we use Horner. For the specialized plot for linear flow, we use MC. For radial flow, for the type curve, we use Agrawalt. Delta T effective. And for linear flow, for the type curve, we use delta T E N L. Okay? That's everything. These two, the specialized plots, are only for buildup. We can't make a Horner plot if we don't have any T sub P. We can't make an MC plot without any T sub P. This is not in the textbook, and this is big. If we only have linear flow, which is in every case I've ever looked at, we may not get square root of K or X sub F because we may not have a prefrac K. But we'll always have this. And very few people in the industry realize that we can get initial pressure on any buildup. It doesn't matter if it's radial flow or linear flow. We're either going to have one flow regime or the other, unless you're dominated by wellbore storage and you didn't run your test long enough. But as long as you broke into radial flow or broke into linear flow, you'll always have on a buildup P star, which is usually very close to initial pressure. And I would say next to permeability, I'll always say that permeability is the most important reservoir characteristic. I'm going to use the word characteristic twice here in the same paragraph. In reservoir characterization, the most important parameter we ever get is permeability. Probably the second most important parameter we get is pressure, initial pressure. Things like H, porosity, saturations, frac lengths, those things are lower on the tier of what's going to be important to me, whether I'm upstream, midstream, or downstream. Yes?
So is that P star the same as our equation P1? It's not the same.
P1.
Well, you have a pressure one.
Pressure 1's a function that back calculates pressure from pseudo pressure. The function pressure was already written for us by the people at LSU, and that calculates pressure from P over Z. And that's how I got the idea of going backwards, reverse engineering, and I used the same secant method or successive approximation method to get pressure from pseudo pressure. Okay, let's make the equivalent of a Horner plot for linear flow, an MC plot. And who's MC? Don't we have a bibliography at the end of every chapter in this textbook? Isn't that the way this textbook's set up? A reference section? The end of every chapter. Let's see if we can't find MC. We already passed it? It's probably no, we didn't get it. It's Milhelm-Chesowitz, and it's probably a sub-reference in here. But if you can find out about this plot at 1 Petro. Yeah. We're on page like 143 or something. What page are we on? Okay. I think that we made didn't we make a square root of time plot? Yeah, here it is. What was that? This looks better. Okay, here's a square root of time plot that I'm borrowing. And now that I have pseudo-time, which remember we're going to always account for viscosity and compressibility from the top of the hour. We're going to do that first. I've done that. The only thing I really had to grab from my problem statement was that initial pressure. And I don't really have to do that. I could always use it in terms that included the units of viscosity and compressibility, but I like it to be in realistic time units. Okay, so let's do MC time. T sub P, F4, plus, times, plus, delta T, all raised to the 0.5, minus delta T raised to the 0.5. Now, instead of plotting this versus the square root of time, I'm going to plot it versus M. Why do I have negative numbers for delta pseudopressure? This was a drawdown. Let's get this. No, we're all right. Let's not go there yet. Let's plot MC time versus pseudopressure. Okay? Yeah, I reused the square root of time plot. On this plot I had two other columns, and now I got the columns of MC time as my x-axis, and that's actually on the rightmost column that's highlighted, and the leftmost column is pseudopressure. You're going to have to speak up. I got these engines running.
Why not using the delta pseudopressure as a deep controller?
Can I just balk? I'll tell you why. I wanted to get the plot done. And also, this is a specialized plot. And on these specialized plots, which I have for buildups, I want pseudopressure, not delta pseudopressure, because I want that extrapolated pseudopressure, which when I use pressure 1 gives me extrapolated pressure, which gives me initial pressure. If I would have been clever, I would have been able to trick you of why I did that, and you wouldn't have had to ask that question. My delta pseudopressure column is wrong. Let's continue on with this logic here. Radial and linear, but we have buildup on buildup and on drawdown. How can I make a new dimension on this? Okay, so this is built, we have type curves we only have to use equivalent times on buildups. On drawdowns, we can just use delta T adjusted for viscosity and compressibility in both cases. Now, on drawdowns, I don't know if this is going to be off the screen or not. Yeah.
When calculating MC time, that delta T in there,
Yeah?
are we supposed to be using the square root of TA or just TA?
What do you mean?
For that delta T, we're not using the delta T that was given to us.
We're using delta square root of delta TA.
Okay.
Is that your question?
But we're not like in the far right term, we're not taking the double square root of T.
No, there's no double square root. Okay. I want to fill in these two things with buildup and drawdown. Delta pseudopressure in a drawdown is pseudopressure I minus pseudopressure of the well flowing. And on a buildup, it's pseudopressure of the well shut in minus pseudopressure of the well flowing. So that's why right now on my computer screen I got negatives for delta pseudopressure. I've got a switch. That's the other reason I tried to cleverly get around getting my plot out without getting this thing fixed first. This is why. Okay, I have to fix this. On a buildup, delta pseudopressure is not equal to C6, which is the pseudo. See, it assumed that this was a drawdown. It assumed that the pseudopressure at time 0 was the pseudopressure initially. Okay? What I want to do is take the pseudopressure of the well shut in and minus the pseudopressure at time 0. Watch what I'm going to do very carefully. I'm going to put my I-beam on the absolute value of C6, and I'm going to F4 it twice. Oops, it wouldn't let me do that. I actually want it relative, okay? Because on a buildup, this number keeps changing. But I want to subtract C6 absolutely. Oops. You see what I did? All I did is reverse the absolute. Now it should be 0 and increasing positive numbers. Okay, we made this plot, but it's not very useful for us because I can't tell where the straight line's supposed to be. Do you see that? Okay, this is what always takes me a long time in class. You guys got to help me. How do I find my straight lines again? What? Where do you see shapes? Shapes. Okay, I don't know whether this is my straight line or this is my straight line. Do you see that? I'm clueless. With my specialized plot, my MC plot, I've got nowhere to go. All right? So what helps me diagnose which flow regimes are where? Type curves. So they don't have to be dimensionless type curves to start with, but that's why I just got my delta pseudopressure type curve done. I got delta pseudopressure, and I got delta T, delta pseudopressure, and I think I don't know what this is. Oh, why is it delta PA over Q? What in the world is that? Well, it says my semi-log derivative. We're not ready for this thing I'm shaking around yet. Okay, this looks like my semi-log derivative. Okay. I should have a type curve with that and the derivative on it. Do I somewhere? Do I have both the derivative? Did I never plot? I think a lot of these type curves don't have derivatives on them. Let's put it on this. Let's copy paste this one. Let's get a raw data plot of pressure and pressure derivative. I'm going to delete my background. And instead of plotting T sub D and P sub D, I'm going to just, because I'm not there yet, I can't get to T sub D until I have some formation properties like perm and frac length. Let's just plot time and delta P. Excuse me. Okay, is this going to be helpful? I didn't calculate nothing. I shifted, I used a log-log type curve, copy-pasted it, got rid of the Bennett type curve in the background, and plotted my raw data, delta T, delta pseudopressure. This delta TA could be delta TA. So now I got delta T on this plot, delta pseudopressure. I'm going to put my grid lines on it. And the reason I'm going to put my grid lines on it is I'm going to look for slopes. And I usually look for half slope. That's 1 by 2 boxes. I just made that's unit slope. Half slope is Yeah, that's right. One box over and two up. And, okay.
Dr. Crowder?
Yeah.
Sorry, I was a little behind. What match points did you end up with?
I'm not plotting T sub D. I'm not plotting T sub D. I'm plotting delta T versus delta pseudo pressure. I'm not making a type curve yet, but I am making a log diagnostic plot.
So why'd you plot it on the Bennett?
Because I already had a log plot there.
Okay.
I'm recycling. I got rid of Bennett. Bennett's gone. I deleted him. First thing I did is...
The header's still there. It's a little confusing.
Ooh. There we go. Okay, now on a diagnostic log plot, besides looking for half slope in my data, which I'm not seeing, I would like to do a derivative plot. Oh, I know what's going on why this isn't working right well. And this is good. So I'm not getting what I want because I haven't done this yet. Okay, so I have delta TA, but my diagnostic log plot, which will become my type curve match once I have my multipliers. It's a buildup, and so I have to not plot delta T, but delta T equivalent, which I haven't done yet. So instead of delta TA, I guess after MC, let's put it in here. Okay, now I'm gonna calculate this, and that's why I didn't get what I wanted. Okay, does everybody see that I don't have half slope? Okay, let's see if I can magically create half slope with the data. Otherwise, you'll get a new teacher next week. I need to be able to reach T sub P. $168 hours. I can reach it. Okay. The equation is T sub P to the 0.5 plus delta T to the 0.5. And we're using our viscosity compressibility. This first point here I got at 0. I'm just doing for grins because I'm really on a log plot. I got to be out of 0, but delta T raised to the 0.5 minus the sum of, and by the way, I already forgot to make T sub P absolute the first time I used it. I'll remember this time. Plus delta T to the 0.5, and now I'm going to pick up the fact the first time I grabbed Q15 I didn't make it absolute. And now I'm ready to copy this down. And so these numbers, 0.08 became 0.53. And, okay, that's because this is the square root of effective time. Now we're going to do your double-double. What I really want is effective time. How am I going to get that? I got the square root of effective time. Square it. I don't know if I'm ever going to need the square root of effective time, so I'm just going to take the whole thing and square it. I may regret this later.
So why would it even give it to you in that form?
Well, doesn't it look pretty that way?
No.
Well, I think it does. So now we still make big movements. See, 43 becomes 5. Okay. Now let's see if we switch from D to G on our graph. From D to G, you may have different letters. Now let's see if we have half slope. Let me double check to see if my line is half slope. It looks like we have half slope early, not late. I'm not impressed so far. It's almost like I made a mistake. My what? I got it. In my formula, you see this last hat 2? I'm squaring the whole thing. Huh? I knew something was wrong. I grabbed the square root of delta TA rather than delta TA. I knew something had to be wrong. What? You think I'm still wrong? Huh? I could have. Okay, now let's see if we got some half slope. Let me make half slope. See, it's always, that's why I put the major grid lines in here, is see, I got 2 boxes by 1 box. It doesn't matter whether it's exactly square. And now it appears that I've got some linear flow in the middle of my plot. I'm not convinced yet. Let's do a pressure derivative. Now the pressure derivative that I got built in here what mathematical function is being used there in my equation bar? Yeah. What does that tell you? That derivative is a linear flow derivative. We actually have to find a linear flow derivative. The semi-log derivative, yeah. Let's see here.
Wait, are you saying that it was the LN is for radial flow?
I'll say this. This is the semi-log derivative was created for radial flow. But we found out that it had, let's go back to our last problem. What did we find out? Here we go. We put it on our we tried to put linear flow data. Well, it was fine. We put linear flow. We put that last drawdown, which went long enough. Again, because it was synthetic data, I never see this. There's two cases this that I went into radial flow. So we put it on this, and what we found out is that our pressure time data, let's do the same thing here. Insert, see, I know where the shape is now, it's up here. I'm going to put half slopes on here. We found, I'm going to make them red. And I'm going to copy. We found that both the pressure data and the pressure data derivative were half slopes during the linear flow regime. Let's see if we get the same information on 6.8. So I don't have the pressure derivative on this plot. Let's put it on there. I've got some extraneous stuff here for my x values. MC, no, we want, okay, I never put a heading on column G. Okay, I think I got it right now though. Now I'm going to copy my half slope. Oops, I think I copied it too many times. I don't know how that happened. Why does that do that? There we go. Okay, do you see that we can utilize the information we got on the drawdown, that using the radial derivative, we get half slope during the linear flow regime, and we get half slope during the pressure derivative, radial pressure derivative. And so my ladder data deviates south, and my ladder data on my delta P, delta pseudopressure, deviate north, and I got derivatives, or my data going both in this deviate north at the beginning of my line. But it looks to me from, watch me get a shape again. I'm going to get a square this time. It looks like oops. It looks like in that area I've got squared, I've got linear flow from my diagnostic plot. Everybody like that?
On mine, it looks like the entire set of data for the derivative
Is what?
on my plot, it looks like the entire set of data for the derivative is at half slope.
Am I doing something wrong?
No, it's just a little bit different from mine. I'm not sure why. Mine fits extremely well.
I may have something. I may have this set up. I'm missing.
I would guess this
No. You see, I've got. I think you've got a good point here. I had it misaligned. I'm with you. Look at that. I'm with you. I actually had my my data offset 1. Okay, so it looks like it's linear flow for all the data except for maybe the first point. But I have trouble with that analysis too, because on my MC plot, it looks like I got 2 time periods.
Well, yeah, don't they both need to be parallel for the linear time period? Like the whole?
Yeah, and I think we're going to do one more derivative here. I think we're going to do a linear derivative. Let me think. The key to what we're trying to do right now is find out which data to cross plot on a specialized plot to get the coupled parameter square root of kxf. Then we're going to plug in that given 0.1 and come up with the fracture length. Then we can define T sub D x sub f multiplier and put ourselves on a type curve. We're not there yet. I'm struggling. I never highlighted G. This is delta T E N L, where T is a symbol, T is regular case, and ELN is subscripted. Okay, I'm going to get this out of here. I think I want another derivative here, because this is my semi-log derivative. I think I might be okay. Let's try something here. Instead of using delta t, let's use my effective time that's based on linear. But you know what? I want to look at them both. I want a comparison. I'm going to add a column. I am going to copy this over. It's going to be all messed up. I still want to use pseudo pressure, so I'm going to grab these boxes back. But now instead of delta TA, I want to do my effective time linear. I never even calculated an effective time radial. I think I'm going to get a flat line. I could be wrong. I can't grab. Must be time for a break. Everybody's scrambling out of here. Not much action there. I actually think I did the right thing, though. Do you see now it's more evident that I have two flow regimes? And I think this is what I like. I think I want that half slope on my linear derivative. I'm using the delta t effective as my time rather than delta t. And I'm actually using delta t on this one too. That's delta t, delta pseudo pressure. And this one is the one I have trouble grabbing, is the derivative using, yeah, it's all right that it's a semi-log, but it's using delta pseudo pressure. That's the one I want. And this is half slope. Okay, my best judgment at this point in time is the area that I've got boxed in is the data that should be on my square root of time plot or my MC plot that should give me the correct slope for x sub f. So let's try that, compare it to the book, and if I'm wrong, we'll take a break. Okay. We have an area where we get the square root of kxf. We have an equation from b sub g, c sub t, and probably some slope somewhere. And here's where we're going to be getting different data. Okay. Actually, I'm okay with the square root of time area because it's an original, an M of P. But I want to grab the data set that looks good on my type curve. I want to grab the second, third, fourth, fifth, sixth point. Second, third, fourth, fifth, sixth point, and I don't want to go past that. Because it looks to me like on that other plot that I've got two flow regimes. Right now, I'm putting my money on that first flow regime. Remember that we kind of cycle through this, and we're going to look at a type curve, and we're going to see if we made the right decision. I'm not convinced, but that's what I'm going to try right now. So there's my slope. Do you have a point before I hit enter?
Oh, just wondering if you were sure that you wanted that last data point.
Oh, I'm not. I don't even know if I'm in the right flow regime. I'm not going to worry about that yet, but keep that in mind, and maybe we can fix it a little bit later. Let's see what we get. And then I really should do the same thing with the same data set for my intercept, so it's easier for me to change this to an intercept than to rechange the things. Now, one thing I like is this 5,000 pounds that they told me might be original pressure is not too far from the 4670. It's not perfect. And we have no radial flow interceptor. I'm just going to delete that. We would have used those to calculate my perm, but I'm giving my perm. I'm tired of looking at those numbers. Now, what does that give us for square root of kxf? It gives us 65, and then I get, if I divide that by the square root of 0.1, I should get a frac length of 206. All right, I'm ready to look at the textbook. $205. Not bad. You're going to have to shout. No, I slid it over. I grabbed one instead of the other. Okay, so what did I do? That's a good question. What did I do? The reason that, I got to tell you, I didn't know what I was doing. I made the best call I could with the information I got. All I did here, my last step, is I dragged this to this. I didn't add a new derivative. I said I don't like that because that's a drawdown derivative. It's a drawdown derivative. I'm going to move it back to the right derivative. The drawdown derivative is a function of delta t. The build-up derivative is a function of equivalent time. Okay? And when I'm sounding real confident now that I know I have the right answer. See that? I was really shaky there for a second. So the build-up derivative then gave me exactly half slope for my early time data, not my late time data.
So that's the point you used. I mean, that was the point you used. It was 5 points.
Yeah, that's how I'm using that box to select it. All that data is on half slope. And I'm not sure why I'm not getting a parallel half slope. Yes?
Can I see your slope again?
The slope I got in my equation right here? I'm in an equals. Here we go. I got the slope of the first of those points right there. That's TA to the square root. Now, I should get the same answer even if I slide this over to here. What's my answer? My answer for x sub f is, we like that. We don't want to do anything that changes that. My answer for x sub f is 206 feet. I actually should be able to get the same number. Yeah.
I don't think you've got the right data points selected.
Okay.
Corresponding to your derivative.
I don't. Is that because some of them are off the graph?
Well, because your derivative data points are offset a couple cells from your raw data. Does that make sense?
Yeah. But also, I'm curious, do I need to...
What I'm saying is you picked your second, third, fourth, fifth, sixth derivative points, but that corresponds to like your fourth, fifth, sixth, seventh, eighth of your raw.
Okay, I just added a cycle. Okay, I'm going to control Z. I was worried that there was a data point below that, but there's not. Okay, so this point right here is 0.26. Do you see that on my rollover?
Yeah.
You probably can't see that. So what point is that? That's my x value on this, it's this point right here. And I'm doing, the derivative that I'm doing here is under and over it. See that? So I really want to start here at I want to start at the beginning. Is that what you were debating?
Oh, okay, so you expanded it.
Yeah, I expanded it because my derivative point is overlapping.
So you expanded your data set to 7 points?
Yeah, yes.
Okay.
Right.
Why don't you fill it up so we can see?
And don't you like the answer? What?
I mean, why don't you fill it up, like, shade with the yellow, and the point is selected.
You want me to shade this?
I mean, the point is selected, why don't you just fill it up with the color?
Oh, okay. Yeah, okay. Right. So it's basically from the derivative, I like between 0.26 and 464. Good call. There's the data I like there. And I'm picking that because this is half slope, right? But here's the thing I just went over. That's actually, you see, pulls from one above it and down here to one below it. Okay? So I'm actually including one above it and one below it. Now, when I am, so my slope is going to capture this data. Let's see if it does. Okay, I actually could get a couple more points. See that? Although I really liked my answer before. I got 224 feet. And the textbook likes 205. I was a little closer to the textbook, but that doesn't mean my answer is worse. Okay, it's 7:30. Let's take 10 minutes. I'm going to pause the recording. Someone's got to ask me when you guys come back, are you recording?
Carter, what did you change to get the 71? 71. What did you change?
That's left over from my template. That's some equation from the textbook.
I appreciate that because I need to post around this thing.
Oh, you know what? Maybe the equation in the textbook has the temperature. No. It doesn't.
Can I see your slope?
Oh, well, you were one step ahead of me, so I didn't change from where he was last time. He pulled this down, right? He went like, decided to come down before he grabbed one points. He grabbed like 2 or so, or something.
2 below where he had before.
Something like that. So I'll go over here. So it's
Wait, Dr. Keller, when you calculated the slope, you grabbed x values of square root of TA? Is that right?
Yeah, but I don't have to do that. I got choices here. I did delta TA to the 0.5. Well, I got highlighted right here. I don't have to. Let's see if I get exactly the same result if I use MC time.
Wait, that was zero pressure.
Oh, I read the wrong thing. Instead of using pseudo time, let's use MC time.
Yeah, I used the Agarwal time. That's why I was so off.
It's a little bit different.
I'm getting 193 feet, and I was getting 220.
Yeah.
Typically, I use the MC time because it's accounting for superposition. Also, I should be able to use delta TELN. What was the number I just got for frac half length?
193.
I should get the same thing here. I'm getting 206. I get 3 different answers.
Yeah, I had a very different answer when I used
the
T.
same as your first one.
Okay. I would say I'm not going to use this. It doesn't account for my produce time.
For slope?
For slope. I'm not going to use that.
What about for your intercept? It's a you're going to use it.
I'm not going to use it for my intercept or anything. We're not using intercept at this point in time. We use the intercept. Oh, yeah, we are because we're getting. Oh. Okay, so I like MC because I can use the slope and the intercept. I can use the slope for perm, the slope for frac length, given perm, and I use the intercept for initial pressure.
Yeah, okay.
That would be my preferred technique. But the delta TELN is the purest way to get the correct slope. And I got a slightly different number. So I'm going to go with F.
Which is?
I'm going to go with MC.
MC.
And then I'm going to use that intercept to get my
But you said if time equivalent is the purest one.
You're going to have to shout.
You said the time equivalent is the best one to use. You just say that I'm using MC.
So whatever you want to mean by the best. I like the analysis that I'm doing right now because one plot has a slope that gives me x sub f and gives me the intercept. I do think this is a little bit purer form for my x-axis, my dependent axis, to get the slope. It's a little purer, but it doesn't help me at all in the intercept. And what I'm getting for the differences in the frac length isn't worth fussing for. It isn't worth me presenting two different graphs. Okay? Okay, so let's, and also the reason I might be slightly different than the textbooks is I don't know their temperature and gas gravity.
Your fracture half length was 193, is that right?
Right now I'm getting 193. Right?
Okay.
Yes.
On your MC, I'm getting
What about it?
the first value I have the same, but then the second value changes.
Do you have R15 absolute?
Yeah.
You said your MC values? What TP are you?
168.
Yeah, that's not on my side.
Okay.
So, Dr. Callard, if I'm trying to wrap my head around all these different time variables, in this circumstance, the TA to the 0.5, the MC time, and the TE and L, those are all one form or another. They're square roots of time, correct?
Let's see. Yes.
Okay, so that's why it's kind of optional. Which,
Oh, no. Delta TEN is not.
okay, then that's going to make a big difference which one we choose, right? I mean,
Wait a second here. Now,
Use TP though.
I see. We should have. Okay. Yeah. I should have to use the square root of delta TEN. Okay. So let's do that. Let's.
Dr. Fowler,
Yes.
should you be recording?
You want me to record?
yeah, go ahead.
Is
Melissa.
that important?
4.2. Thank you.
Personally, I'm fine with you leaving it on the whole time.
Absolutely.
We're recording.
Because we tend to do a lot of
Okay.
stuff during breaks.
Okay. Now, we're recording. Now, right now, I'm using delta T, I'm using MC. And I'm happy with what I got with MC. This is the MC time, and Lee uses this in a lot of his technical papers, so I'm surprised it's not in his textbook. Wilhelm Chesowitz. That's the time I'm using, and it is a square root of time variable. Okay? The units here are, this is good. These are hours to the 0.5. Okay? Yes. Okay. And of course the square root of this is hours to the 0.5. Oops, look at that. It's changed 5 to 4 to 5. Now, if this was a drawdown, this is what we'd be using because we don't have to apply any superposition. This applies a superposition, and this applies a superposition. This one is good because it gives us an intercept that's useful. Now, the one thing that we haven't done yet is look at this, but right now this is not hours to the 1/2, it is hours, right?
Yes.
Now, let's look at it in hours to the 1/2.
Pretty close to the TA to the 1/2.
And it's a little different. Okay, so we have a third look. So I'm only going to look to see how much I change my x sub f from 193. If I change my slope from the MC plot to delta t ENL to the square root. And what was my x sub f a second ago? Was it 193? It didn't even change it. I'm pretty happy with that. Okay. So either are fine for the slope, but I prefer this for my slope because I not only get the frac half length, I get the extrapolated initial pressure. Okay? Now, I still need this data for my type curves. Okay? I use this data for my specialized plot. What's the specialized plot for radial flow? Horner plot.
So if I'm understanding you correctly, when we do, say, our diagnostic log plot, we should use hours, period, because we don't know what flow regime we have yet, so we shouldn't be plotting against square root of time.
No, but we're going to go to pseudo time immediately. We don't need anything for that.
Well, right. Well, I mean, that's kind of a corrected time.
Yeah,
right?
yeah.
Yeah. And same thing with the type curves. We're going to use it in hours, whether it's a corrected hours or regular hours.
Now, I'm interjecting here. You're absolutely right if it's a drawdown, but we have to apply some sort of superposition if it's a buildup. We have to account for the fact that basically our type curves flatten if we don't account for produced time.
Right. So it's, like I said, corrected hours. So it's still in terms of hours and not, say, square root of hours or...
There's no square root of time on a type curve.
Right. Okay. But when we use the specialized analysis, whether if it's radial flow, that specialized curve is going to be log.
Yes.
If we're talking linear, it's going to be square root.
Yes.
Okay.
Okay. As far as I'm concerned, I can delete this column, column G. I like the fact that we get exactly the same slope and the same x sub f. It tells me there's a true link between MC time and Agarwal's effective linear time. Now that I know that, I don't need it. Okay, I think we're ready to move on and look at some type curves.
Yeah. No, I wanted to know too.
5 million.
No, I mean,
What time basis?
Yeah.
What is the final value?
Pardon?
The final value.
For the slope or the frac length?
61.
Oh, I see. You guys can't see it. So my slope's about 5 million, and my using my pre-frac perm, I'm getting 193. And remember, the textbook is coming up with 205. We don't even know if we have the right gas gravity or reservoir temperature, so the fact that we're that close means we're doing something right.
I'm sorry, the intercept, can I see that real quick?
So the intercept should be the same range, because I just always copy it down and then just change the word to the intercept. And then pressure 1 is, got too many pennies, is giving me an estimate of initial reservoir pressure, 4844.
Well, are you using their values or are you calculating?
For everything, no. For calculating square root of KXF, I'm using mine. I'm using my viscosity and my CT. Yeah. Okay, I think we can do type curves. We have a T sub D X sub F multiplier. It looks like we should be able to calculate this, right? We got perm, we got fractaling. Looks like I just did this trial and error last time. Why did I just do this trial and error? Well, let's do it different. Let's calculate our multipliers and then see how they appear. We should be able to get our multipliers from our textbook. No, because they've got everything in PAs. Let's see if the table doesn't have our match points. Huh.
Table 611.
What page?
I don't know. Okay. Cut and pasted it.
I think there's another table just for match we want the linear flow table. Obviously, I'm nowhere close. See, here's the equation we use in the we've been using here. This is 614, and here it is continued. It doesn't have match points, and if we got match points, it'd be after that.
614, or excuse me, 611 is on page 134.
Yeah.
I don't know if that's applicable to what we're doing.
Okay, let's one page. What page? What?
134.
I think we could make it work with RWA equals x sub f over 2. You know, it seems to me that they did have.
Yeah, it's got fractured well type curves.
Okay, well that tells us, okay, right. Okay, so where I've got my mouse here, this would tell us if we did a match point, how we'd get our fracture length. So here's our point, here's our T sub D coefficient, K, times delta T, but see, we have an x sub f, right? 193 feet. We know what 2637 is. We know what K is. We know what phi mu C sub T is. So we should be able to get our match point. Let's calculate it. If we've never done that before, let's do it right now. Okay. Every time I hit function spacebar, I'll think of Gene. And then I have to, where's my snippet tool? It should be readily available. How come it's not? What? I can't work and think at the same time. I am going to now try to calculate my T sub D multiplier. Now, what's your question?
It looks like the same equation in the problem except we're using the aggregate wall time.
For delta T, I'm going to use my delta T ENL. Okay, that's a good point. Let's see what we're using right now for T sub D X sub F. It's times our multiplier, and what time is it? It's delta T EA. We know that we're going to use this number. Okay, so let's correct our column first, and then let's calculate our multiplier second. Okay, so I'm going to pull out a piece of paper and do some algebra here. You can do the same thing. I've got to get delta T over T. Do not use LF, use X sub F, dimensionless multiplier, right? And then if I divide, actually I want that upside down, but it doesn't matter. I'm going to leave it that way because it's going to be easier. Equals X sub F, I'm looking to the left, and then I'm going to square X sub F, and then I'm going to divide it by 0.0002637 K, which I've had over phi mu C sub T. So I'm going to try to do that calculation right here. Equals X sub F squared divided by, open a paren, 0.0002637 times K, which was given to us 0.1, there's no T, divided by, open another paren, phi mu C sub T. Phi times mu times C sub T. I'm using a gas saturation 100% in this problem because I don't know what they did here. Close a paren, and I get 916. And I think I'm upside down. I think that that gives me delta T over delta T XF, and so I don't want to multiply by L3. I want to divide by L3. Well, you know what? I think I'm better off doing a 1 divide. Okay, there's my T sub D X sub F. Calculated, not trial and error. I'm going to go take a sneak peek at one of my type curves, okay? Now, I don't have my P sub D yet. Did I guess this? See, I guessed this. Now I got to do my P sub D work. But let's guess it first and then do the work. Here's a nice type curve, right? I think I divide by P sub D, so I want to divide by a smaller number. Let me see if that's right. Yep. And even a smaller number. It's not looking very good on my type curve. But remember, we've got more than one flow regime, but this could be good. I'm cutting it in half again. Okay, I actually like that last thing I hit. See that? It's telling me that I got a frac conductivity of what? A what? 25, right? So I just tried a couple. Now we're going to calculate. I did a trial and error. We're going to calculate our true P sub D multiplier because we have it. But I like to rush to judgment. That's just what I do. So why does the first part of my data fit on my type curve and not the last part? We already know from our diagnostic type curve that only some of our data was half slope. Only some of our data was linear flow. So we're either transiting into some boundary dominated flow or some other things. Okay, I'm guessing that when I get the right number calculated for P sub D, it's going to be about 5 times 10 to the 7th. What? I think I have the wrong type curve, maybe. It's T sub D versus P sub D.
How did you change the T sub D again? I think you made a change to it. Yeah, you changed it to the Agarwal time, right?
Yeah. Oh, yeah. Right. Oh, yeah. I see your question now. Yeah, I'm using Agarwal. Effective. It's accounting for T sub P, right? I'm accounting for the produced time, right? See the produced time over here, well, it's covered up now. I'm accounting for the produced time. So I've done two things. I've changed the equation and I've changed the constant to get it on my type curve.
No, what I mean is, like, sorry, you got a coefficient on, say, the column under PD, but did you...
I trial and errored my PD. I haven't calculated it yet.
What I mean, like, I just, for my case, like, I use a TDXF, but the TDXF doesn't have any relationship with the coefficient that you calculate that. I mean,
Well, if you're still got one that's for radial flow,
no, I mean, you calculate this column with, this one, did you use the type?
I'm not using that number.
Oh, okay. You didn't use this 0.1.
This is a T sub D over C sub D.
Yeah.
I don't even care about that. I'm going to delete that. I'm never going to use that. That's left over from radial.
Yeah, but did you use the TDXF? Did you use the 0.06 is not the one you calculated, right?
Ah, what did I do here? Did I do something wrong?
Yeah, I mean, it's not calculated correctly.
Oh, I see what you're saying. I've got this. I've got the right thing for the wrong reason. How does that sound?
What do you mean?
This data right here is Okay, see, I should be using this number I calculated, right? Isn't this your point?
Oh, you put it in the wrong box?
Yeah.
Okay. And that's the reciprocal of...
Okay, yeah, and now let's change my P sub D. So let me do this here. I think this has to be a little bit bigger. Then we're going to try to calculate this number. I think that's about where we were. Okay. You caught me good. Okay. Here's T sub D x sub f. Here's the number I calculated. So what I want to do is delete this 0.006. See, I'm not using it anywhere. I calculated my T sub D coefficient in the wrong box. Now I've got what I'm plotting. And now I can truly get rid of this column. I'm not using this column. This is a rollover from a T sub D. Well, you know, I used it in my last example because I actually had linear flow that rolled over into radial flow. Okay? I actually had some radial flow. I actually needed a T sub D over C sub D coefficient. If I ever do need that, that'll be rare. I can use example 6.7, but I'm not going to delete it. You know what I'm going to do with this? I'm going to gray it. I just don't think I'm ever going to use it as a template. That's what I tend to do, is I just gray it over. Okay. Let's try to calculate our P sub D over, and then I think we don't have to use this table.
So there's no value to that in a linear flow analysis.
Well, there was, because you see on that last one I actually ended up putting, because I had linear flow followed by radial flow, so I put my ladder data on a T sub D over C sub D type curve. In reality, no. You'll never see linear flow roll over to radial flow. Only with computer simulated data that they have in the textbook will you.
Do you think it's possible this is what we have going on in this particular example?
We don't know yet. I think it goes into boundary dominated data, but I'm guessing ahead. Now let's go find our, because it doesn't appear that we've ever done this, let's find our P sub D coefficient. Pseudo pressure versus time, I think we're right here. Okay, I want to calculate that number I just used from this equation right here. I'm in table 611 on page 134, the lowermost right equation. It's, oops, what was that? 134? It's a good thing I said that out loud. 143 maybe? Why does that do that? Oh. Where am I? Here we go. Pseudo pressure versus time. You see, they're using the type curve match point to get perm. We've got perm. Let's get the match point here. And of course, what we're trying to do is get either a number by about 9 times 10 to the 7th, or it's reciprocal. Uh-oh, I think I grabbed the wrong thing because I see a mu and a z. How did I do that? I see I grabbed the one above it. I made a mistake there. Let's go back down here. I got to get rid of this equation. It's got a mu and a z in it. I got to go back to my equation down here. This is what I want to snip. I want to get the P sub D over delta pseudo pressure match point. And let's see. I eventually want P sub D. I think this is going to give me the reciprocal again. So I am going to probably calculate this, and I'll probably get a number with a negative exponent, and then I'll reciprocate it. Okay. We want the match point, so we're going to take K, multiply it by H, divided by 142.22 QGT equals KH. I think I got K covered up. Where is it?
Should be up on the right there. It's B or something. To your right side.
Oh, right there. K times H divided by 1422 QGT. I think I got a mistake here. I think I just... There we go. Let's try this again. Equals K times H divided by 1422 times Q times reservoir temperature I'm with you. Okay, and I got something to the -8, and so I got to take this where I suspect it, so I got to take 1 over this. And now I think I had a number about 9. Where's my, now let's take a look at my type curve. Okay, so we've done this forwards and backwards through the weeks of work here. This type curve match was not trial and error. We were given perm. We found the linear flow period. From the linear flow period, we got the square root of KXF. And then we had fracture half length, so then we were able to calculate the P sub D coefficient and the T sub D X sub F coefficient. And so we placed our data on our type curve. I'm going to play with this for a second. Okay, it isn't?
Did you change your time basis for TVXF? Is it supposed to be? Yeah, it has to be based on the actual time. That's what made the difference for me.
I'm playing with the size. And let's solid fill these with red. Okay. Now, you notice that nothing I did affected the level setter. I mean, I kind of got there earlier on, but now I'm actually able, from this particular Bennett type curve, I'm actually able to determine the fracture conductivity. The only thing that went into getting my data on this plot was my calculation of X sub F in the given perm. I calculated, I didn't trial and error, my level setter and my east-west X setter, okay? So I should be able to directly observe what the frac conductivity is from this plot. And it looks like it's a little higher than 25, doesn't it? Right? The data is below the line? And the textbook, what do they come up with? What page is our problem on? $146? Oh, it's on page 136? Oh, I see. I see what you're saying. I'm with you. So they're getting something's wrong here. Oh yeah, 6.5. They don't calculate frac conductivity? Where are we? Here we are, example 6.7. We just 6.8. Okay, here. Here's where we got our 205. Do they use this type curve right here? I don't see any date on it. Then they go to example 6.9. Well, we can calculate it. They came up with the frac conduct. Oh, you know what? They're using an old definition that has pi in it. Oh, yeah, CR of 10. But their CR is different than our CFD. Their CR has a pi in it. So 10 times pi is 31. Are you with me?
Is the graph on page 145, is that what they're using?
Yeah, okay. Here's their type curve match of 6.8. Here's what, oh, you know what? They don't have any data that differentiates from the type curve match, which means that they only have one flow regime. I'm not sure why our data and our derivative but the point I'm trying to make is their CR is different than our CFD by pi. So when they're getting a CR of, when they're getting, what is that? When they're getting a CR of 10, that's our CFD of 31.4. Because there's a pi, extra pi in the original definition. And I'm not using Cinco's type curve, I'm using Bennett's, and I'm still perplexed why my data deviates at the tail end from that. So that's yet to be resolved. Pardon? Huh?
Are they going to use data points? The range? Yeah, I think, let me see it. Mine indicates the way you're seeing.
Yeah.
Where the tail kind of comes up.
Yeah.
Desirable, is that what we're looking for? Or?
I'm trying to explain why mine does and their doesn't.
Yeah. You're calling for TXF. And I kind of understand how the way people are. I just wonder, is that what's that? The basis for that dimensionless time is the aggregate time. And we have to use the aggregate time.
Let's try to answer this with one fell swoop. I have never agreed with the textbook on pseudo-time, although mine agrees with the original paper. Let's see if it's just a function of pseudo-time, okay? I'm curious. I have a theory. Let's just make, I'm going to save this. Let's just make pseudo-time real time, okay? Everything's done with pseudo-time, right? You see what I did? I'm over, oh, you know what, it's not going to change, let me change any part of an array, is it? Let's go like this.
You know they've got an entire table of data they calculated for this.
I know it, but I can't match it. I can never match it. Now let's use real time instead of pseudo time and see if that affects our no, it doesn't. Actually, I'm pretty happy with that. So it's not an error that I possibly have with pseudo time that's affecting my data to kick up off the curve at the end. So I'm just going to Control Z and Control Z and Control Z again. That I just tried a theory is all I did there. Okay, we got more than one type curve to look at. I think this one should be all filled in for us too. Yes. I can put finite conductivity data on a Green-Garten type curve. I've got to realize in my brain that it's not going to fit on that line. We know from this type curve what happens, what's the difference between infinite conductivity, which is that bottom line 500, and a finite conductivity. I know, okay, I got to use my brain focusing capabilities here and realize that the data on the Green-Garten type curve is going to be slightly above the infinite line. But let's see if there's anything else that's informative about this type curve match. Basically, it's telling us that we have very early time, and it's telling me that I am, you see, where the data deviates is at the end of linear flow for x sub e over x sub f. So it looks to me like it's possible that what we're looking at is boundary dominated flow, but I don't know why the textbook example doesn't show that. What? What I did a second ago, Gene, is I replaced this column with this column. I got rid of pseudo-time to see if my pseudo-time, which I calculate, which is different than the textbook, is affecting my interpretation.
When I do the TDXT and I use pseudo-time, I get a straight no.
Right now, you got a type curve where it doesn't deviate.
Yeah.
Right. And I know it's not
that's what the book's doing.
Yeah.
Maybe there's a square root of time here. We should be using this. Agarwal time accounting for T sub P in our time. That's what I'm using.
Yeah, but if you change it to the pseudo time,
Which
it goes straight.
I'm telling you that if you're using a drawdown type curve, you've got to use superposition and account for that. Now,
That may be what the textbook.
okay, now the other thing, you know, I'm a detective. That's all I am. Maybe they gave us the wrong T sub P. You see, if I change my T sub P to be a bigger number, it will have less effect. Watch this. Okay, my data deviates up and away from my type curve. Down here is my T sub P. 168 hours. Now, let's make it, multiply it by 10. You see how the longer, remember that thing that you can always use 10% of your build-up data directly without any correction for superposition if your build-up data is 10% of your drawdown data. So the bigger I make T sub P, the less it affects. The more it does what you guys found out by yourselves, that if you just use delta TE, that you get the same result. Now, what else could I do to check this out is remember that T sub P is going to affect my P star on my MC plot. Did this most recent investigation change my extrapolated pressure on my MC plot? We were told it's close to 5,000. See, look I took it from below that. Watch this. My extrapolation using the 168 hours gave me a number a little bit lower. Let's do this. Since I love goal-seek, data, what-if analysis, goal-seek. Let's change this number to 5,000 by changing T sub P. Okay, now if I say T sub P is 704 hours, I get a perfect, still tails up maybe a little bit away from my last lines, but it's really hard on this type curve to tell what's going on because they end most of those lines. But now I get exactly 5. So maybe the real error in the problem assignment, and there's some typos in the error, is what they use for T sub P. Now, the other way to investigate that is they've got tables, right, of if they went from equivalent adjusted time, from time to equivalent adjusted time, they didn't use any pseudo time, did they? Then we should be able to figure out what they use for T sub P. But they gave us a T sub P, didn't they? Where is it? How could it be above it? Huh? Oh, I see, in the next row, 168 hours. Okay, I think we've analyzed this as much as we can. I don't have near enough time to go over the tests tonight. So we'll postpone that for next week. But remember, my idea is that hopefully the lessons learned tonight will diminish the amount of questions that we have on the test. Because, you know, we're really just doing the same thing that we did over the last section, only we're moving from radial flow to linear flow. But all these things about superposition for build-up versus drawdown, those concepts are the same in linear flow as they were in radial flow. Okay? So let's end this now. We'll pick up with another example. It won't take nearly as long, and we'll start with the key for the last quiz. And then that way you can pull up your test, I'll open up the quiz, and we can see where we may have any differences. Yes?
Initially, you pulled the regating type of. What did you do? What was the name? What did you use to achieve?
What?
Drainage area. Sorry. I said you pulled out the regating type of.
Green-Garten type curve.
Initially, what was your aim? Is it to achieve the drainage area?
What is what?
I mean your aim for pulling it up.
My what?
Your aim, your objective.
Oh,
What are you trying to explain?
nothing. It's there. It's got T sub D X sub F, and it's got P sub D. And I've got those variables. I'm going to look at it. It's already there. But you know what we haven't done is we haven't looked to see if there's maybe some other type curve that we need to look at. But I think we've got... I don't think that there's any other type curve we need to look at for linear flow, but I was just seeing if there was some information on that that might help us. As it turns out, I don't see anything. Do you see anything that's going to help us? Yeah. I don't see anything that's going to help us. It looks, well, yes I do. It looks like it's either still on linear flow or it's leaving linear flow and going into boundary dominated flow, but that's because I artificially changed my T sub P. The way I'm going to leave this, I'm going to change this back to the T sub P that the textbook gave us. But while you're asking the question, remember that's going to curve it up some more at the tail. Now let's go back and look at the Green-Garten type curve. It's not helping me. I think the textbook and I are not quite in sync with... There's either something wrong with the data or I'm massaging it right, but I mean we hammered the fracture half length. Yes?
So bottom line, sum this up. From this example, what did we determine with confidence? Even if it's limited.
Okay. That's a good question because I want to make this point. We're not going to get those true half slopes unless we have infinite conductivity fractures.
Okay.
So they're going to be close. They're going to be close. I like this example primarily because it's more realistic as to the idea that most of the stuff we look at has finite conductivity fractures. In fact, the number 30 is real close. If I have to pick out, if I have to start with a number on a trial and error basis, I always start with 10, frac conductivity of 10. And then maybe I look at some plots and then maybe I improve it. So here's where we started. We got half slope. I don't know why that moved. We got pretty good frac half slope early. So on our derivative curve. So we started there, step by step here. We started here, then we selected that data to do our MC plot, because we already looked at a square root of time plot and saw that there was two potential linear flow periods, right? Early and late. I don't know what that is, but I'm getting rid of it. Okay? I didn't know which one of those flow periods might be. This is a common situation, whether it's in radial flow or linear flow. You got two straight lines. Which one's right? So I go to my diagnostic plot. My diagnostic plot says the early one looks like it's half slope. I'm looking for near half slope. Yes?
Well, is 2 the max that you can get on that plot?
You mean, I know I get 3, 4, 5, 6, 7, 8, 9, 10. Believe me, I've seen it. You can get more than one slope. So the diagnostic curve really cycles around. I go from the diagnostic curve, go to my specialized plot. My specialized plot actually kicks out values like perm and frac half length. Then I come back to my type curve. So except for the fact that, you know, I have this little discrepancy with the textbook on their data not tailing up, and my data tailing up, I think I've hammered.
Is that the same? Are they using a Bennett? Is that what they're
No, I think they're using somebody else. Cinco-lay. Should be the same.
It's very similar.
Should be the same.
So our assumption in we're doing a linear flow for the time equivalent equation, and it being different from the radial flow, that is what we want to do. Right. I guess for the Agrawal, there's two equations for the time equivalent.
The equivalent time, you know. If I'm just giving you some pressure time data and you don't even tell me anything about the well, like, you got to realize in these problems here, it always gives us something. A pressure buildup test was run following a fracture treatment. Okay, yeah. Well, I'm going to first look for linear flow. If someone gives me something, we just drilled this well and we perforated the casing and we ran a buildup, I would probably look for radial flow first. So I usually look for one versus the other first, but I can eventually get to the right answer by trying everything. But all the problems you're going to be given in this course, you're going to have at least a hint. But like on the last thing, we were told it was a fracture, but it ran, what, almost a year on the buildup? Or it was a year-long drawdown, so theoretically it went into radial flow. So you had both linear and radial flow. We can do a little more work with this one with the, oh, I didn't mean to do that. We can do a little more work with this one with the frac conductivity as an intercept of this plot. This, not this one. I've deleted the one. But I can, if I'm just plotting early time, either delta T or delta TELN versus delta pseudopressure, that intercept should have something to do with frac conductivity. Infinite frac conductivity, my early time data should intercept, my early time MAP should intercept my actual flowing pressure on infinite. And that difference should be proportional to my frac conductivity. It's not in the textbook, but it's in the Bennett paper that this type curve came from. All right, we'll end it there. I promise I'll start the next class with the test key, try to resolve any differences, but I'm glad we did it the way we did, because I think that you have a better foundation. That and taking the last test should make more for better targeted questions as we look over the review the last test. Okay? I figured out the whole problem, guys.
Glad I stuck
Hit record! Hit record!
Look at my equation for T sub D x sub F. You see this 24 in it? T1.
What?
Okay, what I did is just open up my book from last year. And you see how my type curve looks great?
You've got the same spreadsheet from last year?
Yeah, I just started over. I didn't look at my last year's. And it looks like,
Do you mind hitting record, or is it too late?
yeah, I'll make some note here. What am I doing here? See, I've got my EL. Which is ELN squared. Egg-all linear. I think what happened here is, where's my cell that has T sub P in it? Yes. Okay, so last year to get a perfect answer, I multiplied T sub B by 24. So are we sure that
Was that days?
was that days?
What?
I bet it was days.
What?
You were pretty close on that goal seat
You see,
with
yeah,
going about it then.
yeah. How do I get this back up here? Transient pressure analysis. Where's my book? The textbook. Page 134, right?
400.
It says hours.
Okay, well that's all I have to do. All I have to do is multiply.
Did not.
All I have to do is correct hours to days,
That's
and
a
I get the right answer.
Typo in the book.
Typo in the book.
Wouldn't be the first.
That's how I did it last year. So I multiplied T sub P by 24. There's 168 days, not 168 hours.
But the test is still built up for 168 hours.
Yes.
That is confusing.
So did you get 10 or 25 on
Okay, I'm gonna run through this.
Did I get what?
those? Did you get a conductivity of 10 or 25?
Option multiplying 24.
See, here's this plot I was talking about making. Is I got a CFD of 26.
No difference.
No, it was my lake time that was, was troublesome. But see, look at here's my type curve from last year. It looks perfect.
Basically what you were telling us.
And all I did, you can see, the first thing that I could figure out is when I was doing my looking at my type curve variables,
Oh wow.
well, it's a division problem, so my constant TM10, but my Horner time here is 4032, and I took 24 times H1. H1 is 168. I used a T sub P of 24 times 168 last year. Anyway, that's all right. I'm not going to leave anything up on that.
So did you not save any of those changes?
That was a different worksheet.
Okay, so you didn't make any changes
I
to your
didn't make any
code.
changes to my worksheet. I looked at last year's worksheet, and I can see that I multiplied my 168 hours times 100. I made 168 days.
Okay.
And that way you're not going to have your data deviating on your time curve. We're not going to get any different results because we used our early, what it's going to let us do though, it's going to let us use more data on our regression analysis. More of our data will be on the straight line, on our MC plot. And we will get a better P star, which is going to be closer to the 5,000 pounds, which is where I found out when I did my goal seat. Everything's fine. One little typo in the book.
Dr. Carter,
Yeah.
so for the exam curve stuff you given, is it based on these two tests? Is the average of the each percentage?
H2 test. So if you didn't take one of the tests, you're not really on the graph.
No, what I mean is, for example, first one got maybe 55 or 60%. this time I got maybe 80%. Is it the average or this?
Yeah, it's the average.
Okay, average
Yeah.
of these two, right? Okay.
Yeah. Well, all you have to do is you can download your grades from D2L and you can figure out where you fit on that curve.
Okay.